Good morning, everyone. Today we're looking at Unit 2, Lesson 8, Action at Zeros and Sketching Factored Form. So we've looked at polynomial functions in this unit, and we've talked about some key features that we can identify from a polynomial function. We're going to now use those key features to help us do a rough sketch of a polynomial. So we're going to look at first a polynomial in standard form or expanded form, and then we're going to look at it in factored form. And sometimes we need to go to factored form to identify some more of those key features before we can graph it. So our first function is f of x equals x cubed minus 2x squared minus x plus 2. So what can you determine about the function? So in this form, in expanded form, what can we determine? Well, we can determine our degree, right? Our degree is just our highest exponent on the x variable, so we have a degree of 3. We can figure out the sign of our leading coefficient. So in front of our x cubed is just a 1, and we have a positive 1 at that. So the sign of our leading coefficient is just positive. Okay, and based on our degree and our sign of our leading coefficient, we know our end behavior. So those two tell us our end behavior. We know that a degree of 3 is going to have opposite end behaviors, and if it's positive, it's going to go down on the left and up on the right, like a line. Okay, and we can also write that as x approaches negative infinity, y approaches negative infinity. As x approaches a positive infinity, y approaches a positive infinity. I'm just going to erase this. It wasn't very clear that that was a negative. It's a negative infinity. The last thing that we can tell while we're in expanded form is that our constant on the end represents our y-intercept. So we would say we have a y-intercept of plus 2. Okay, to work towards our domain, our maximums and our minimums and our x-intercepts, we're going to need to factor. So I'm just going to bring this down here where I have a little more room, and we are going to factor. Okay. In order to find our x-intercepts, we need to factor. So let's rewrite our function down here. So we have f of x equals x cubed minus 2x squared minus x plus 2. Okay, so I have 4 terms, so I'm going to factor by grouping. When we have 4 or more terms, we should try to group some things together and try to common factor out of them. So if I group x cubed minus 2x squared together, I can common factor out an x squared from those, and I'll have left x minus 2. For my second grouping here, a negative x plus 2, I'm going to common factor out just a negative 1. So then I'll have left an x minus 2. So I've kind of created that common bracket that now I can pull out. So I'm going to pull out that common bracket of x minus 2, and then I'll have left x squared minus 1. And I can't do anything more with my x minus 2, but this is a difference of squares. Right, so this is a difference of squares of perfect squares. So we can common factor that as well. X squared minus 1 will become x plus 1, x minus 1. Okay, so we can identify our zeros. I'm going to put my zeros over here. So my zeros are going to be, from x minus 2, I have a positive 2. X plus 1 means my 0 is a minus 1. And from x minus 1, I'll have a plus 1 for my 0. If we want to identify the multiplicity that goes with those, we'll just do that underneath. Okay, so looks like my 2 has a multiplicity of 1. It only shows up once in the equation. And so do my other zeros, only have a multiplicity of 1. So that means they're going to cross at all of those points. All right, so let's draw our zeros in first, and then we'll work on identifying our domain range and our maximum and our minimum. So if we have zeros at 2, positive 1, and at negative 1. Okay, we've discovered our end behavior is going to start down. It'll be down on the left, and it's going to go up on the right. We also know we have a y-intercept at 2. And from each 0, we should cross the x-axis, and then we'll come back down where the next x-intercept is at 1, and we'll cross back over that x-axis and come back up to cross at our other 0. All right, so looking at this graph now, we should be able to identify our domain and our range. So from graph, we'll identify our domain is going to be x for all real numbers, and our range is going to be y for all real numbers. If we look at our maximum and our minimums, well, we don't have any absolute maximum or minimums because we have endpoints going in the opposite directions. So we're going to say we have no absolute max or minimum. But we do have some local max, right? We have, I'd say this is a local max. So we could say we have a local max. For y equals 2. And we have a local min somewhere down here. Okay? And it looks like it's going to be somewhere between 1 and 2. So we're going to have a local max, or a local min, around 1.5. So if we substituted in 1.5 into our original function and calculated that, we should get a negative 0.625 for our local min there. So we'd say we have a local min at y equals a negative 0.625. Again, our drawing is just a rough sketch, so even though my minimum went lower than a 0.625, I was just doing a rough sketch, and then when we actually plug in what's between those two zeros, it'll tell us what our local minimum should be. All right, so that's for the first one. Let's look at another example. This time we're already in factored form. So let's see if we can identify all these key characteristics. So in factored form, we have f of x equals negative x minus 3 times x plus 2 times x plus 2. Okay, so if we want to identify our degree, we'd have to pull out how many x's do we have. Let's take a look at how many x's do we have being multiplied together. So we have x times x times x, which equals x to the power of 3. So that's going to give me my degree of 3. My leading coefficient, right, is that coefficient at the front of my polynomial. If I was to expand this all out, I'd still have this minus 1 in the front. So I have a negative leading coefficient. So our degree in our leading coefficient sign tells us which way our end behavior is going to go. If we have a cubic, so a degree of 3, let's just write we have a cubic, our end behaviors should go up to the left and down to the right. Right? They should match that of a line sloping down. So what else can we tell? Our x-intercepts, we could tell. So if we have x minus 3, we're going to have x-intercepts of positive 3. And then x plus 2, we're going to have an x-intercept of a negative 2. And then we have another x plus 2, so that's another negative 2, 0. So that tells me my multiplicity on 3 is going to show, it only shows up once, but that negative 2 shows up 2 times in my equation. So that's going to have a multiplicity of 2, which means it's just going to touch the x axis. All right. And finally, we could tell our y-intercept, right? We could sub in x for 0. So if we subbed in x for 0, or 0 for x, we're going to end up with a negative, and then in our first bracket, we'll have a negative 3. In our next bracket, we'll have a positive 2 times a positive 2. So this is all going to equal A negative 3 times a negative 1 is a positive 3. 3 times 2 is 6, and 6 times 2 is 12. So that's going to be our y-intercept. So let's plot some of these things, and then we'll see if we can identify our domain range and maximum and minimums. So we have zeros at 3 and at negative 2. Okay, we know our n behaviors on the left-hand side is going to go up, and on the right-hand side is going to go down. Now we take a look at what's happening at these zeros. Well, we know that this one has a multiplicity of 2, so it's just going to touch, but does not cross, right? Because it has a multiplicity of 2. So it's going to touch at that point, and then it's going to continue back up. We also have a y-intercept we should plot. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 will be somewhere up here. So from that x-intercept, it's going to go all the way up to my y-intercept. And we don't know that it's going to turn at that point. It could go, and I bet it looks like it might go a little bit past that before it starts to come back down to my other 0. And then at that 0, it does cross because it has a multiplicity of 1 and continue down. All right, so let's talk about our domain and our range. Again, we have endpoints going in either direction. So our domain is still going to be x for all real numbers, and our range is going to be y for all real numbers. If we look at our maximum and our minimum, again, because we have n behaviors going in opposite directions, we don't have an absolute maximum or minimum, but we do have some local maximum and minimums. So I have a local min here, right, and that also happens to be one of my zeros. And this local max, if it's between my two zeros, well, my one zero is at negative 2 and my other one is 3. So right between those two would be f to the 0.5. And if we sub that into our original equation, we should get 15.625. Again, we're just guessing that the local max will be right in the middle of our two zeros, but that's a fair assumption to make. So that's going to be my local maximum. So let's write those here. So we have a local max at y equals 15.625, and we have a local minimum at y equals 0. Okay, let's take a look at a few more examples. So you should pause the video now and see if you can fill out most of the chart except for a domain and range and maximum and minimum. See if you can fill out the rest, and then we'll get back together with it all filled in and go through the graph of this. Okay, so here's the next example all filled in. We went through everything we did with the previous two examples. One thing I want to point out is that this function has a multiplicity of 3. Okay, so when it has a multiplicity of 3, the graph is going to flatten or be tangent to the x-axis at that 0. So we know our n behaviors on either side of our 0 to the left are going to go down. And we also have a y-intercept at negative 1, so let's plot that there. It's going to go down, but it's got to cross that y-intercept we have as well. So we're going to say it's going to cross it like that and then head down. But you can see that at the x-axis, it's going to flatten. It's almost going to become parallel to the x-axis before then it continues up, something like that. All right, so that's what it means when it has a multiplicity of 3. It's going to flatten or become tangent, which means parallel to the x-axis at that 0 and continue up. For our domain and range, we're still going to have x for all real numbers because we have n behaviors going in the opposite direction. And the same is true of our range. We're going to have y for all real numbers. Our maximum and our minimum, we have none. Okay, we don't have a local max or a local min, and we also don't have an absolute max or min. All right, so pause the video again and try to go through all of the features for the next one and see if you can graph it as well. Okay, so here's this one all filled in. Couple things to notice is that we had a degree of 4. If we counted all the x's in our equation, we had 1 in the first bracket, and then another one in the second, and we have 2 because we have x to the power of 2 in that fourth one. So we do have a 4th degree polynomial here, and our leading coefficient is negative. So I just put that at the front so that we knew that we have a negative 4th degree, because that will tell us what is going on with our end behavior. Okay, if we identify our zeros from our factored form, here's the zeros that we get, and then we have to look at their multiplicity. So what is the exponent on them? And they're all 1 except for the 3 has an exponent of 2, so it's going to just touch the x-axis at that 0. We could also identify our y-intercept by subbing 0 into our equation, so we're going to get 9. And then that tells us that our end behavior both are going down because we have a degree of 4 and it's negative. Okay, so we plotted those on the graph. It's going to cross at -1, go all the way up to my y-intercept at 9, come back down to my next x-intercept at +1, and then it'll just continue down and back up and touch at our last 0, which is 3, but it's not going to cross there. It's just going to touch and then come back down. All right, so in this case, we do have an absolute max. And again, these are just estimates, but it looks like it happens right around our y-intercept at y equals 9. We also have a local max, and that looks like that's happening at y equals 0. And then finally, we have a local minimum. And we're kind of guesstimating where that happens, somewhere between our zeros of 1 and 3. So if we substitute in a 2 into our function, because it looks like it's between those two zeros, we should get a -5 at that point. So that's your local min. That's it for your notes for today.